let's take a look at more about electric fields. And this content is going to be analogous to the material that was in the More About Gravitation video. And the reason why is because it turns out gravitation and electric forces are very similar. They're both inverse square forces. So if I write down the force expression for gravitation over here and the force expression for electric force over here, you can see they have similar formats. There's a constant out front, here we have two masses, here we have two charges, and both of them are proportional to the inverse square of the distance between the two objects. So they have similar behaviors and we can treat them with similar concepts. So we're going to start out with electric potential energy. We're going to say that if we have a system that's made up of many charges, then when those charges are infinitely far apart, the electric potential energy of the system is equal to 0. Now, if they are infinitely far apart, it makes sense, right? Because then they have no effect on each other. They're not interacting with each other, and so the potential energy should equal 0 when they're infinitely far apart. Another way to think about it is the electric potential energy of a system is the work that's required to bring the charges from infinity to their current locations. Now, we have an expression for the electric potential energy between two charges. So if we have a pair of charges separated by a distance r, the electric potential energy is equal to k q1 q2 over r. That's given in your data booklet. Now notice this is a little bit different than the gravitation expression, because in the gravitation expression, the gravitational potential energy was always negative. Here, because charges can be positive or negative, the electric potential energy can also be positive or negative. So for example, if we have two positive charges, well, the expression would give us an electric potential energy that's positive. If we have two negative charges, we would have an electric potential energy that is also positive. And if we had two opposite charges, a positive and a negative, then the electric potential energy then would be negative. So electric potential energy is positive if we have like charges, and it's negative if we have opposite charges. And we can create a graph of this, put electric potential energy on the vertical axis and distance between the charges on the horizontal axis. If we have opposite charges, then we're down here in the fourth quadrant. And if we have like charges, we're up here in the first quadrant. And in both cases, it's a hyperbola. Now, what if you have more than two charges? What if you have three charges, q1, q2, q3, separated by these distances? Well, just like with gravitation, the electric potential energy is equal to the sum of the electric potential energy of each pair. So it's equal to the electric potential energy associated with charges 1 and 2, plus the electric potential energy associated with charges 2 and 3, plus the electric potential energy of charges 1 and 3 together. Now before we had this thing called electric field, and electric field was defined as the force per charge at a location. And now we're going to have this thing called electric potential. Electric potential is the electric potential energy per mass at a location. And the unit here is the joule per coulomb. You can see that from the equation. And if you remember back to circuits, a joule per coulomb is a volt. So this electric potential is the work per unit charge to bring a test charge from infinity to that point. And when I say test charge, all I mean is a very small charge that's not going to have an effect on the system as a whole. Now we have an expression for the electric potential caused by an isolated charge if you're a distance r away. And that's given by this. The electric potential is equal to kq over r. And this expression is given in your data booklet. And just like we did with gravitational potential, we can have equipotential surfaces with electric potential. And that's a surface, of course, which has the same value of the electric potential all around it. So if we have an isolated positive charge, for example, the equipotential surfaces would look like this. They'd be circles that are centered around the charge. And if it's a positive charge, then the electric potential is going to be positive if you're closer to the charge. And it's going to approach 0 if you're an infinite distance away. And the electric field, let's draw in the electric field around this positive charge. Notice the electric field lines are perpendicular to the equipotentials, just like they were in gravitation. And if we do the same thing for an isolated negative charge, well, here's the negative charge, and the equipotential surfaces would be circles around that. And as you get closer to the negative charge, the equipotentials are going to have lower values, more negative values of potential. And again, and draw in the electric field lines like that, and the electric field lines are perpendicular to the equipotentials. Now let's do the same thing if we have parallel plates. Let's put a positive plate up above, a negative plate below. The electric field would look like this. It would point directly from the positive charge to the negative charge. And if we do that, let's see, we'd have equipotentials that look like this, and we'd have high potential near the positive plate and low potential near the negative plate. And we have an expression for the electric field. The electric field is equal to the negative of the gradient of the electric potential. Now this is given in your data booklet. And notice that the equipotentials in this case are equally spaced. And I did that on purpose because the negative of the gradient then is constant. So the electric field is constant, which makes sense. We've seen before that the electric field between two charged plates has to be constant. And we can draw this as a graph. If I have electric potential here and R right there, the electric potential would increase as we increase R. So the gradient here, let's see, the gradient is positive, so the electric field is the negative of the gradient. Well, let's see, if the gradient is positive, then the electric field then is negative, meaning that the electric field points down, which agrees with what we'd expect between these two plates. Now let's say that we have a charged conducting sphere. So a charged conducting sphere with a positive charge on it. Well, if you remember back to what we've seen before, if I have positive charge on a conducting sphere, the positive charge is going to be only on the surface of that sphere. And it's going to arrange itself so that the electric field inside the conducting sphere is zero. The electric field lines would look like this. They'd be radial and away from the surface. And the equipotentials, well, let's see, the equipotentials would be perpendicular to the electric field lines, so they'd look like this. They'd be concentric circles with the center of the conducting sphere at its center. All right. Let's think about the graph of the electric field and the graph of the electric potential. Well, let's see. So if I have electric field versus R here, where R is the distance from the center of the conducting sphere, well, inside of that conducting sphere, the electric field is zero. And then once I'm outside of the sphere, I have a graph that looks something like this. It's proportional to 1 over r squared. Because outside of the sphere, the electric field is that of a charge that would be at the center of this conducting sphere. The electric potential graph, however, would look like this. Inside of the sphere, it would be a constant value, but it would be positive. And outside of the sphere, it would look like this. Outside of the sphere, it would be proportional to 1 over r. Now what if you want to know the electric potential at a location and there's more than one charge affecting your potential? Let's say we have two charges and you're these distances away and you want to know the potential at this location. Well, just like with gravitational potential, the electric potential is equal to the sum of the electric potentials caused by each charge. So the total electric potential at this location would equal the electric potential caused by Q1 plus the electric potential caused by Q2. Now I'm going to write down another expression. I'm not going to derive it right here because it's very similar to what we saw in gravitational potential ideas. But the work that's done in moving a charge across a potential is equal to the charge that you're moving times the change in the electric potential. Now, I'm going to say that a little bit differently. The work that's done in moving a charge is equal to the charge times the potential difference. Well, wait a minute. We've seen potential difference before. If I rearrange this a little bit, the potential difference is equal to the work per charge. That is an expression that we saw in circuits, and in fact, it's the basis for what we saw in circuits.